So welcome those of you online to the ASEG plus the GSA here down in Tasmania, not the ACT as it says on the slide. We're going to start off with a bit of a welcome from the GSA group. Thank you.
Hello everybody, and lovely to see quite a number of people in the room here. Yeah, this is our Tasmanian division, local division get together, and we're having it with the ASEG, and they are making this a very special event, which is great. And I think John is a member of both organisations, so that's fantastic. Just a quick reminder that there is a field trip to Cygnet, and John's involved in this as well. So if you need very detailed information, you can talk to him about it. But yes, bus leaves here at 8 AM this Saturday, the 30th. So if you still want to come along, please register. Have we still got room?
Yes, we do.
Okay. Please register, and you can find that information in the newsletter and on the website. The other thing is we have our next talk in May is from Tony Webster, and he'll be joint meeting with the Royal Society of Tasmania, and that will be on a Sunday, the 15th of May, so a little bit different to usual. Also will be live streamed, and it's at 3 PM in the afternoon. And I think we're going to have it here rather than in the Royal Society rooms because we've got a bit more space here than they have. So more information on that will be coming on the website soon. So that's really all from me. And I'm going to hand over now to Matt, and he's going to do the introduction. Thank you.
Thank you so much, Karen. Welcome, everybody. My name is Matt Cracknell. I've been roped into chairing this session, which this evening we'll have John Bishop talking about geothermal energy potential in Tasmania. A couple of housekeeping things. Firstly, the ASEG acknowledges the traditional owners of the land on which we gather today, the Palomina, and the many lands on which we undertake our work. We recognise their continuing connection to these lands, water and culture, and pay our respects to their elders past and present. There are a number of corporate members. We'll just skip those pages because and there's etiquette. There are people online. Please be respectful in the comments that you make. I will ask that because we don't have a really good speaker set up here, I'll ask that any of the online communications are done through the chat. I'll be monitoring that throughout the seminar, and I'm happy to read out people's questions in due time. There's a whole bunch of membership benefits for being an ASEG member. You could even become one of the executives. Oh, you just missed out because we had our AGM this afternoon. Keep in touch. Now, so we've got that over and done with. I'll get rid of that, and I'll open this up, and we'll go from there. So welcome, John. You did give me some things to talk about you, to introduce you. But it's quite difficult to find stuff on the internet about this John Bishop, but I found a whole bunch of other things. Apparently there is, on Wikipedia, you know, there's an English comedian who's way more famous than this John Bishop, unfortunately.
It is.
The founder of a US-based motorsports sanctioned body, the International Motorsports Association. Founder of Dreamland Barbecue. An English cricketer from the earlier 20th century.
None of those are me.
None of those are you. A member of Parliament for Wycombe in 1430. And my particular favourite was a body snatcher in the mid-19th century, part of the famous London Berks gang. Apparently, John Bishop went around digging up cadavers and selling them to physicians. Yeah. Anyway, this John Bishop is way more interesting. He started his professional career with the New South Wales Geological Survey.
I did.
There you go, I got that right. Industry, joined Geophysics department at Macquarie University. In 1980, you founded MITRE Geophysics, which is still going today, nice and strong. You also co-founded Icon Resources, which was a tungsten producer in ASX in the mid-2000s-ish.
Yes.
And Riverside Energy Chairman. But the reason that we're here today is that John Bishop was the co-founder of Couth Energy with Roger, what's that? Roger Lewis in 2005 and has been a keen disciple of geothermal energy ever since. Kuth listed at the ASX in 2007. And the most important thing is, and we'll hear a little bit more about this tonight, is that John and Kuth defined 2 large inferred geothermal resources in Tasmania and a third in Vanuatu. The need for reliable, renewable energy with 0 emissions has never been greater. So thanks, John, for coming and being the inaugural Energy of the Future presenter for the ASEG.
Thank you, Matt.
Good evening, attendees here and in Zoom land. Let's see if that brings that. The aim of having geothermal resources is so that we can produce electricity from. Thank you. Yeah. So we have enough heat and enough water that we can use the geothermal energy to produce electricity, and Australia is leading in the application of renewable energies by far. We have more wind and solar per capita than anywhere else in the world. But having said that, we still got 60% of our energy comes from coal at the moment, but that coal is rapidly being retired. And even with more and more wind and solar, we're still going to need and I've got to find the right term for this. Even wind and solar is predictable to a large extent, but we'll call it dispatchable. By dispatchable, we mean that you can provide the power that you want. The demand is there 24/7, but it will go up and down. So it's baseload plus, if you like. We still need some of that. And what are we doing to provide that at the moment? We're getting larger batteries. We talk about long-term storage for batteries, but that's still only for a matter of a few hours. And we have pumped hydro. Pumped hydro exists and pumped hydro is planned. And we also have gas, perhaps gas as an interim measure, since we won't get to 0 CO2 with gas, but it's considerably less polluting than coal. What we don't hear anything about is geothermal. That is not presently in the mix of reliable energy. And that's the reason that I put this slide up. It enumerates some of the attributes of geothermal, but a little bit on perhaps why geothermal isn't there. 10 to 15 years ago, there was a concerted focus effort on geothermal in Australia. There were 8 listed companies, $500 million spent, and there were no power plants eventuated from that exercise. And so the mantra is that geothermal doesn't work in Australia. We certainly don't lack for geothermal resources. And I think we've got here in Tasmania one of the best, as I'll attempt to explain. But some of the attributes, it's the only renewable that doesn't require any storage. It's got a very, very small footprint. On your screen, there's a tiny little red dot down here, and that's the geothermal footprint for the same power, same amount of megawatts for solar, wind, etc. It's got by far the highest capacity factor down here at the bottom right-hand corner. Capacity factor is the amount of time that it will actually produce its nameplate capacity. So if you've got a 100 megawatt plant that's geothermal or nuclear, you'll get about 95 megawatts out of it year in, year out. Whereas if it's solar, you'll get 20 to 25. So you're getting 4 times the amount of power for the same size plant. The aim eventually for geothermal, that the earth gets hotter everywhere with depth. So the aim is to produce geothermal power wherever it's wanted. But to do that's going to require routine drilling to around about 10 kilometres. At the moment, we've got routine drilling to about 5 kilometres. So in the meantime, until we get to that state, we will be seeking highest temperatures as close as possible to the surface and close to demand. A little bit of background Geothermal 101, just said that the Earth gets hotter everywhere with depth. In fact, it's got an average gradient of 1 degree per kilometre. So we've got a temperature at the centre of about 6,000 degrees hotter than the sun's surface. And that heat from the Earth is partly due to its the primordial heat of the Earth's formation, going from a gas to a liquid to a solid, generate a lot of heat. And then the other contribution is from the heat from the decay of radioactive isotopes. Those radioactive isotopes are mainly potassium, uranium, and thorium. And at the surface, they occur mainly in granites, granitoids. Though such granites are sometimes called thermally anomalous granites or heat-producing granites, or as they're sometimes called, and I like to call them, couth granites. And the bottom diagram down here at the bottom right shows the distribution of that heat loss from the Earth's surface. About 45 terawatts of power is being lost to space. Mostly the large amount of heat loss is on the plate margins, with perhaps a tenth of that in the plate centres. And this is, so it reflects plate tectonics, or the heat flow distribution in the Earth drives plate tectonics. So it'll come as no surprise that most of the geothermal power plants are along the Earth's margins, which in this diagram are in red. But the point of the diagram is that all of these listed power plants have a temperature below 210 degrees. So they actually, between 72 is the lowest temperature plant. There's, here it is, it's nearly half a megawatt of plant in Alaska with water that comes out of the ground at 72 or goes into the plant at 72, and the highest temperature is 205. That's about the temperature range with the 200 mark that we expect to get in Tasmania or in Australia. So the point of that is that there's a lot of plants that can act as precedents for what we wish to do here. And those, I don't know how many there are, 50 or whatever it is, less than 7% of the Earth's geothermal capacity is represented there. So Audie said that we want to find areas that are hot and close to the surface. The less drilling we do, the better. That's the major cost of geothermal is in the drilling. If we go to the Earth's margins, the plate margins, then we often get surface emanations of geysers, boiling mud ponds, hot rivers, etc. There's usually some surface emanation. But if we're at a plate centre, such as Australia, then we have no surface indication. I just should say that in the plate centres, it will be a granitic source of heat. Mostly, we do have in southwestern Victoria, we've got volcanics that are 5,000 years old, and that's contributing. There's some use of geothermal, not for power, but for direct heating in southwestern Victoria. But as a generalisation, it will be the hot granites, the couth granites that will be driving the geothermal projects. And the best analogy for that is an electric blanket on a bed. If you have an electric blanket without a doona, it's not terribly effective, and you need a doona on that blanket to be effective. And so it is with a granitic source. And you need 3 to 5 kilometres of sedimentary cover to get these large temperatures at around about 5 kilometres. So here the maximum temperature, which is one of the spots there in the Cooper Basin, of 235 degrees. But unless you drill and perhaps get some artesian hot water, there's no surface indication. So you're going to, if you're interested in doing this, you need a concept, and then you'll need some geophysics to define it. Just summarising what it takes to develop a geothermal power plant is really 2 things. One is the amount of brine that's being produced out of a well in kilograms per second. So if you've got something like 60 or 100 kilograms per second at say 200, then you're going to get something like 8 to 10 megawatts of electricity per well. In blue on there, I've got two projects, one in Cornwall in England that's got 60 to 70 kilograms per second at nearly 200 degrees. And then typically Upper Rhine Graben is there at slightly higher rates of flow rate and slightly higher temperature. Also shown on there, but not terribly well. In fact, I can't see it at all for some reason. I can see it on the monitor, and on the monitor it shows an ellipse that comes round like that. For some reason the grey hasn't picked up, and the ellipse extends out about that far. So there was the maximum flow rate for the previous Australian projects was less than 30 kilograms per second. Good temperatures. The temperatures were up to here, getting close to 250 or a bit above 250, but very poor flow rates. So that was the reason that no power plants were developed from previous Australian. And we can see that here in the, if we go straight to this is the classification. Geothermalists are very good on acronyms, and the classification of geothermal projects can be, geothermal plays often called, can be quite confusing. But I think for our purposes, we can keep it very simple. We can have hydrothermal, hot and wet, or wet and hot, petrothermal, rocks, hot rocks, but really meaning hot and dry. And this is the hot and dry scenario where we've got a hot granite, a couth granite at depth with a certain amount of sedimentary cover. And given that amount of cover, given that it's relatively old, the opportunity for having high permeability is naturally occurring high permeability is rather low. And there's been quite a lot of research which started in the 70s, but this was the Australian goal 10 to 15 years ago, was to enhance or engineer some fractures at depth in the granite, pump down cold water into that fracture zone, and then extract hot water from it. And as I've just shown, the flow rates were too low to be viable. They're about a third of what was required. But up here in the top right, we've got the low-hanging fruit of plate margins. We've got volcanic sources, got active or recent volcanoes, preferably with a bit of a clay cap so that the boiling water is constrained. You put a hole down through there and the steam comes up and can directly drive the turbines. But our Tasmanian target is the one down here, down at the bottom right, where if we think of having a large fault, a large, wide, broad fault going through the granite or beside the granite, then we'll have, and it's a heat-producing granite, it's a couth granite. Fault contains a lot of water. We have a naturally, it's a hydrothermal, non-volcanic hydrothermal system, and that's our target. Before we say yes, we've got it, let's have a look at the geological setting for Tasmania. Tasmania actually consists of two separate plates with a paleo plate boundary somewhere through here. It's under cover of more recent sediments of the Tasmania basin. But in the Devonian, we had a large number of granites, fertile mineralized granites for the main part were emplaced. They're shown here in red where they outcrop. And there's a series of contours going down to 9 kilometres from work done by David Lehman. He did that by the gravity, and just put the Booga gravity in here so that you can see the correlation between the granites are lower density, and so you've got where you've got a low density, then the likelihood is that that's caused by a near surface granite. And then lastly, a regional geological map showing the Tamer fracture system, as it's called there. Then 50 million years ago, we have Tasmania came into an extensional regime with spreading, grabens filling with sediments. And as Ron wrote nicely in 2019, you've got to, I'll go back one. This black spot here is the Lamont resource, which we've put in for reference. Most of the diagrams will have this Lamont resource. That is the larger and the more attractive of the two geothermal resources. And you can see that it has, this red lines are the major fractures from Ronberry 2019. And here we have an east-west transform fault in which it would be expected to have a high fracture permeability. And then lastly, from a heat point of view, we'll see that Tasmania does have abnormally high heat flows. And perhaps one reason might be that Tasmania, most of it, is sitting over the interpreted East Australia plume system. So when Roger and I started talking about this, whether Tasmania was a potentially good site for geothermal exploration, and that was in around about 2003 when Geodynamics had just listed and was looking in Central Australia. This was the possible geological scenarios, which you've got the Jurassic dolerite and the Upper Palmina in green, the dolerite in buff, then the Lower Palmina in a light blue, and then maybe you've got some the thinner metasediments, or maybe you haven't. Maybe you've got straight underlying granite. Maybe it's a normal background granite, or maybe it's a Couth hot granite. So these, and Roger also postulated a possible porous layer at depth. So they were, what would that look like? And taking those 5 different scenarios, and if you don't have a hot granite at depth, then you get a background of 80 milliwatts per metre squared, which is about the Tasmanian background. But if you put a hot granite in at depth, then it jumps up to 120. And the interesting point here, the point that I want to make is you can have the same surface heat flow, high surface heat flow, but this one with a greater thickness of insulating sediments gives a higher temperature at a shallower depth than does this one over here. So that's the one that we would like to see, and just remember the 120 milliwatts per metre squared that Roger calculated. Now, most geothermal projects in Australia started with a background database from oil and gas, showing deep oil and gas holes, showing high temperatures, particularly in the Cooper Basin, but not so in Tasmania. We did have 6 legacy heat flows, of which some were very, very high. So the continental average is 60. We've got one here that's a little bit low and one up here that's 2.5 times as high. And so that was encouraging that Tasmania had a high, overall high heat flow. The other thing that was relevant was the Tamar fracture zone. And it was known from work done by Dudley Parkinson, an academic here, the university left in the end of the 70s, I think. And some of his students and others had done work up here at the northern end of the Tamar fracture zone and had shown it to be electrically conductive. And so that's the Tamar conductivity zone. And one of the most likely source of having an electrically conductive zone is that it's very permeable with a brine in it. Hot salty water is very conductive. So we decided to go ahead, and eventually we voted a company and got some money. And the first thing that was done was a regional heat flow program. This was a series of holes, cord holes drilled to 250 to 300 meters deep, and waited until they had they'd settled down, equilibrated, and take the temperature at the bottom of the hole, determine the thermal conductivity of the overlying rocks from the core and their heat generation, and produce a heat flow. Notice that the maximum recorded was 118, very close to Roger's postulated 120, which was good to see. Disappointingly, the Tamar fracture zone up here at the north, which would have been a lovely place to have an electrical power plant with all of the industry up in the far north, that was cold. But down here in the middle of in Tasmania's Midlands, it was very high. This 118 is some of the highest, one among the highest heat flows recorded in Australia. So it was a really good thing to have, plus the fact that the Tamar fracture zone came through it. That heat flow data was given to Hot Dry Rock Proprietary Limited, and they produced a thermal model here, which assumed a conductive heat. To get the model to match the recorded data, they had to introduce this, they called it Unit A, which was to get the high heat flows that were, this is the outline of the heat resource, the Lamont resource. It's possible, at least I think it's possible, that in fact this is a permeable fracture where we've got convective heat flow rather than the conductive heat flow of the model. Okay. So we've established at this point then that we've got a high heat area. We now need to establish that we've got permeability so that we can get the flow rate. To get permeability, we already alluded to the fact that you can have high permeability on fracture zones. So we need to map the structure. A detailed aeromagnetic survey was done. More detailed gravity was done, and this is the digital elevation model here. And this diagram down at the bottom right-hand corner is a result from a fault stress programming modelling that was done again by Hot Dry Rock. And this is showing that at 5 kilometres at the intersection of two faults, which you can't see on the screen, I don't think, but there's a fault, northwest running fault and a northerly fault. Where they intersect, there's the tension, there's tension rather than compression. So that's a potential point for having enhanced permeability. This diagram here, where I've put that stress point on, it comes from Tom Osterson's PhD thesis, which I'll refer to again. But we've got a series of dipping and intersecting faults, good thing to have, right in the centre of the geothermal heat resource. The other way to map permeability is directly with geophysics, and you can magnetotellurics, a geophysical electromagnetic method. Depending on how you do it, you can go down and see as deep as the Moho, or you can get better definition within the top 5 kilometres, which is what we did here with Couth Energy. And this is the resistivity scale from less than 1 ohm metre in red up to over 1,000, over 2,000 ohm metres, highly resistive in blue. And right in the middle of the resource, we've got a large red zone, which we hope is permeability. Hope it's due to a brine saturated fault or fracture. But there are other possibilities for getting low resistivities. It could be sulfides. It could be graphitic shales. Graphitic shales certainly a possibility this is at 3 kilometres depth. So it's getting into the granite where graphitic shales are unlikely. But Gerrit Olivier did for us a passive seismic velocity survey, of which these are the results. The stations, the geophones are little black dots, and this is the a depth slice of the anomalous velocity at 3 kilometres. And you can see you've got good correlation between an anomalous low velocity here that matches the anomalous low resistivity or high conductivity, which gives you confidence that it's very likely to be a high permeability zone. These are two different models, and each model is made up of a series of bricks or three-dimensional blocks. And some lovely work that Tom Osterson did was to where we've got a low resistivity cell that coincides or nearly coincides with a low velocity model, then he puts a black dot. And here's the black dots, here's the coincidence, and this has got a depth range of somewhere between 1 kilometre to 5 kilometres. And if we put them in there with the mapped shears, we've got these black dots are closely related to this north-south shear, and this zone here has been cunningly covered by a green little target dot where these two faults intersect. And there's the positive tensional shear. So that, I hope, says, righto, it looks like we've got good permeability. We've got good permeability, good heat flow. We can go back to this diagram, a flow rate, have a stab at a flow rate for that good-looking permeability and calculate a temperature at 5 kilometres, 4 kilometres, and that suggests that Lamont will be somewhere in this region here. Perhaps that dot happens to be around the 7 megawatts per well, which is the global average for geothermal. The 7 is the average, but there's a large range. The highest was 52 megawatts for one well. It may well be higher now as we go deeper and deeper. And so that's looking very promising. That's looking great. We've still got a little bit more work to do before we want to drill. In particular, we want to look a little bit more deeply into to how deep the granite is. We want to drill into the granite, drill into the heat source, and magically on this display, there are no contours there whatsoever. They're still there on the PowerPoint, but with actually you can see the black contour numbers. So there's through the resource of Lamont outline, we've got a variation of granite depths from about 2 to 7 kilometres, which is a good range to have. It's achievable, it's doable, and okay. So if you then so we've got heat, we've got permeability, we've got a right sort of depth range. If we put all this together, as Tom has done rather nicely from his thesis and outside of his thesis, this is a plan view showing the depths to the granite and showing the postulated high permeability zones from the black dots plus the structure. And we've got here a nose of granite that comes across with a permeable zone at the end of it. And if we do a perspective look here to the southeast, these bladders or lozenges, if you like, these are isosurfaces that are less than 1 ohm metre, and they're pink above the granite surface, and they're grey in the granite. And then we've also got the inferred structure as well. And the blue dot is where one might test to see if all of this interpretive, and it is still interpretive at this stage, to drill down to there to see if we get what we would expect. So, and then from that, there's the model is drilling down to the resistivity low in the magnetotellurics with a interpreted geology that's got a Kuth granite at depth with a fault that cuts off the edge of that granite that's dipped steeply to the west. That's where one of the faults would seem to lie, the north-south one, where it cuts across the granite roughly east-west is where it's most permeable. And you would have a play there where you extract from depth and inject back into the surface. And there is a case history looking very much like that underway at the moment in Cornwall. The Cornish play, which is down here, this is the heat flow from the granites in southwest England. they actually did get to 120 milliwatts per metre squared compared to the 118. That's within the error of the measurement. They drilled down to a vertical depth of 4,500 metres, re-injected at 2,500, this is early days, a minimum flow rate of 66 and a temperature of 188. And that's on its way to delivering some. This is the power that it's going to put out, which I don't believe that's the limitation from the geothermal attributes. It's the possibly the existing network, or if we put a smaller one on to start with, it won't cost as much. So, in summary, Lamont's got all the right attributes. It's got a hot granite at the reachable depth. It's got a large code-compliant resource. It would appear to be nicely permeable, and it's got lookalikes in Germany and in the UK. But we still haven't been rushed off our feet with people wanting to build a power plant with that. But I think this is where it's going to change. Is a new kid on the block is called direct lithium extraction from geothermal brines. There's a lot of efforts going into this, and it's moving very quickly, and it's already happening. And this is the reason that there's a lot of excitement about it. Here's the lithium demand curve. Here's the lithium supply curve with a large gap. And getting your hold of lithium is exercising particularly car makers and battery makers and the like considerably. So geothermal brines contain, we'll have a look at how much lithium they contain, but this slide is mainly concerned with showing how lithium derived from geothermal brines is better than hard rock mining, which is mainly in Australia, or from evaporative players in South America. Again, the footprint is remarkably smaller, much smaller. There are no CO2 emissions from geothermal brines. That's a good thing. And there's very little water wastage. Clearly, water wastage in clay evaporites in South American deserts is not a great thing. But I think the important thing is that it's going to be a new source of high grade, high purity, battery grade lithium will be turning up very soon. How it works is there's a number of different technologies that are being tried, and it would seem that each different project with its own temperature and its own salt concentrations has its own special way of looking at it. But take a standard geothermal power plant, extract the heat to drive the turbines, and then before you re-inject, you have the lithium extraction, and it can be one or more of a mixture of these. This is a good reference if you want to know more about this. Then the National Renewable Energy Lab, Ian Warren's paper in late 21 is a good paper. This isn't such a clear diagram on the right, but what it purports to show is that this is the whole of Western US. Here's Washington State up here. And this is a legend of lithium from 0 up to 440. And there's only 3 or 4 geothermal sites out of some hundreds of sites that's actually got significant lithium. And similarly, this is a different legend scale in Europe, but we've got high values in Italy and high values in Germany, and some up in here, which I'm not quite sure where that is. But the point is that it would seem that most geothermal plays do not have high lithium. And why should we expect that Tasmania will have Tasmanian's granites are mostly in the northwest. A lot of them are mineralised, fertile granites for the between Fingal, which is the other geothermal resource in the northeast in Tasmania. Here's Lamont. We've got some outcropping granites here, which they're assaying. That's hard rock assaying, 100 to 250 ppm, and we go up to nearly 1500 ppm further to the north in Tasmania. And the advice that I've been given is that the actual lithium won't be a problem. It'll the factor, the important factor, will be the flow rate. And got here taken the English example, which is also now running as a lithium project, and the German Graben Valley is also running as a lithium project. This one Unlimited is out of in Germany as well, in the Upper Graben. So we've got 200, 250, 200, and here up in the Salton Sea in California, much higher temperatures, much higher flow rates, but not that much higher concentration of lithium. And it seems to me that if you do have lithium, you're going to have a value of around about 200 ppm. But having said that, there's a geothermal project, a plant in New Zealand, which runs at 14 ppm lithium, and that will also is looking to extract lithium, not only lithium, extract other metals as well. So if we change the goal, our aim is now to produce lithium and electricity from geothermal energy in Tasmania, then indeed we might be getting warmer in the search for viable geothermal resources in Tasmania. And apologies to Ron Tamberg, he really wasn't talking about geothermal energy when he penned that cartoon. And many thanks to the people who have helped this project forward. Some of it has been for many years. Thank you. That's it.
Thanks very much, John. I'm willing and able to take questions from the floor and online in Zoom. Mike.
One thing you talked to me about some years ago was the potential for direct usage of the heat in other ways. But have you gone cold on that idea now in terms of direct usage for heat in, say, agricultural purposes, greenhouses, all those sorts of things?
No, I think that will still happen. What was difficult with that was the try to put a value on what that would. So you've got a breakdown. You've got the brine, and it's cost 10 units to produce to bring to the surface, and we might be able to sell it for electricity for 5 units, but we still need another 5 units to break even. And was that 1 unit for a fish farm and 2 units for a glass house, etc., and 1 or 2 units for a spa? But no, I think that will happen, absolutely. And there's some very good examples. The very best example is a place called the Resource Park in Iceland, which has got and the Resource Park has the Blue Lagoon off it, which I'm sure you've all heard of, and it's a splendid place. The last time I was I had a guided tour of the Resource Park, which couldn't go into the Blue Lagoon. It was booked out for a week. There was no more people allowed in, but a whole lot of industries were hanging off the power plant, and greenhouse, glasshouse, and fish farming. Even fish farming would barramundi are the go-to fish for fish farming. Very tolerant at wide range of salinities and temperatures, but they would die in the Macquarie River, for example. So there would be no risk of ethnic contamination.
We've got a question online. The question is from Jess Godfrey. How far from electricity transmission line is the resource? I guess this is our other infrastructure.
Yeah. It's a couple of kilometres from the distribution network, which can take up to, I think it can actually take to 30 megawatts, but you can put 5 to 10 megawatts in there without too much difficulty. So well, that's actually, yeah, it's under the wires is the glib statement. It's very close for distribution. Because it depends where we're going to drill. That is still, we could drill here, we could drill there, and we'll be within a couple of kilometres of the distribution grid. The transmission line is another matter. So if we want to start producing 50 megs or 100 megs, then we're about 50 kilometres from the transmission lines. That's expensive.
Leo, did you have a question?
I have a question. What percentage of energy would go to pumping water by duct? Is it substantial percentage?
It is significant, yeah.
Can you just repeat the question?
The question was how much energy would be, well, the question was how much energy for pumping the water back into the ground, but it's also likely that we would actually have to pump out of the ground as well. So there'll be pumping up and then pumping back in, and it's significant. It could be 20%, 25%, something like that. Yeah, quite a bit.
And so that energy production, which is stated, that's already the surplus, or it's the total production. You need to subtract
the 7 megawatts was net, but it's an estimate.
Right.
It could all be whichever you. I'm a geophysicist. What would you like it to be? You know? Don't laugh.
All right. Well, now so there's a geology question.
Oh.
From Nick Doreen. Given the Tamar fracture zone was cold from the Kooth drilling, why is it conductive? Best model now?
It's still permeable. So in fact, we did do a line of so the question is, you take that Tamar zone, why is that conductive? It's cold, so it's not hot brine that's up there, but it's relatively cold brine. It's going to be still 30, 40, 50 degrees, 60 degrees at 2 kilometres. And so that's certainly warm enough with a reasonable amount of dissolved salts to give you a conductive pathway.
Question from the floor here.
Yeah, I'm just wondering, you've got like the Henbury and Hicks Creek granites there between your Fingal and Lamont areas, and that's the one you're taking your lithium values from, is that?
Well, they're just the nearest ones, yeah.
Right, and do you have any evidence that they might be subsurface as well in getting towards the areas that you're interested in? Given that we repeat the question, the question is that I've taken values of lithium in outcropping granites that are 50 kilometres away from the two resources. We've got the Royal George granite, for example, and the Henbury, and what's the third one? Gibbs Creek.
Gibbs Creek, yeah. Those lithium values in that little patch of granites, we could go back, I think, and have I gone too far? Here we are, yeah. Whoops, we haven't gone far enough. I haven't got a scale on this. This is about 50 kilometres from Lamont to the outcropping granites, and then 30 to 50 kilometres here. And these are mineralised. There's tin mines in here, and they're what we would call fertile granites containing significant lithium. We maintain that because these are heat sources here and here, both running at over 100 milliwatts per, that it is fertile. They are fertile granites underneath, and we could expect them to have similar properties to many of the granites in the northeast that are outcropping. So these are the closest. They're not close, and they're also not the only ones that have got lithium in them either. And those in the game have said it's not likely to be the lithium's your problem, it'll be the flow rate. And you need a high, because it is only 200 ppm, not a high value. You need a large volume through there to get significant tonnages out of it.
So there are a number of other questions coming online. One from Princewell at the moment is, are there risks of seismic activities during the project?
Are there risks? There have been risks with geothermal and particularly in the drilling. And also we talked a little bit briefly about engineered and enhanced geothermal when you're trying to stimulate the fractures to make them better. And so you're pushing water down and you'll get a microseismic when it did that. There's a lovely video of geodynamics pumping water down, stimulating a well by pumping water down and having a whole lot of seismic sensors. And you can see the fractures growing and growing with time. And it's a nice thing to watch. So that's a seismic event. There was an event recently, might have, I'm guessing now, between 2010 to 15, there was a geothermal project in Basel, right in the city square, and there was a 3.8 seismic event that was induced from the geothermal, and that closed the whole thing down, which I thought, well, that was a bit much at the time, but then I read a bit, and Basel, in fact, was flattened in 1667 or whenever it was by an earthquake. So they're a little bit sensitive about earthquakes, but that project has since started again. So they're now doing it a little bit more carefully, a little bit more sensibly. Short answer is, with this type of geothermal project with an open hole, some seismicity is possible.
Any more questions in here? Otherwise, I'll go. Yeah.
You mentioned a temperature of 72 C up to 220, wasn't it? At 72 up to 80, up to 90, what can you do with that's very hot water, but it's not going to drive a turbine, though, is it?
Yes, it does. That was the point. Yeah, in fact, it's driving nearly 0.5 megawatt. The way it's done is that it's called a binary system, which just means that there's a heat exchanger, and you have water coming up at 70 degrees that heats up a working fluid that is a gas/fluid. Heated up to 70 degrees, it becomes a gas, drives the turbines as a gas, vacuum on the other side as you condense that gas, and yes.
What gas would that be?
It's a common gas is a mixture of water and ammonia, and that the ratio depending on the temperature. But there are other pentanes and butanes and the like as well.
So there's another question. We can continue on, I guess. Taking questions.
Sure. Yeah.
From Craig Anderson. Great talk, John. Can you please tell me the resolution of the detailed gravity surveys carried out? And was it detailed enough?
Yes, of course. Not to say we couldn't do more. I presume Craig doesn't mean what was the station spacing of the gravity, and they were a random walk on wherever we could get access. So it wasn't a grid of every 100 meters. And it was done to David's specifications. But we would be, and what I didn't mention, I think I mentioned, that if we do a joint inversion, and by when I say we, I mean Kerrit does one day for me, a joint inversion of the passive seismic velocity with the gravity, we'll get much better handle on the shape of the discontinuity. So between the granite and the Mathina, and then between the Mathina and the Tasmanian basin. And that'll all come out of the joint inversion.
All right, excellent. Any other questions from the floor? I'm kind of, going between
You're doing well.
Land and, floor land. No questions there. Okay, there's a couple more. From Ralph Bottrell. Have you looked at the Arthur Metamorphic Complex, which is a deep-seated structure that has a lot of alteration focused along it, partly blanketed by basalts?
No, it's a simple answer, Ralph. There has been some work done, or there were some exploration licenses around the Heemskirk and Federation granites by Allegiance. So Lindsay Newnham was involved in that, but that's a fair way south from the Arthur lineament. But thank you, that's an interesting thought. Yeah.
What percentage of the
Yeah,
profits?
of the lithium. Yeah.
Another question from Luke Smith online. What is an optimistic total megawatt output for a fully operational plant with many wells? Is it a multi-well system?
Yeah, it would be a multi-well system. It's another topic, but it's one that's dear to my heart. A new development in geothermal application is to have a closed loop where you drill a U-shaped hole into the ground. You line that hole with a material that keeps the fluid in it. You fill the loop up with 99% water and with a little bit of sealing agent. And you do it in such an area, you drill it down 3, 4, 5, maybe even 9 kilometres where it's very hot. The water heats naturally and you get a natural thermosiphoning. So there's no, the right word escapes me for the moment, there's no power loss due to extracting the water and pumping it back down. It's a natural thermocycle, and that is, with using that system, we can make a very good estimate as to what the power will be per cubic kilometre, per square kilometre on the surface, and potentially we can get gigawatt output from that. And from one output, one setup, say one football field, for example, we might have potentially 50 megawatts from one setup, one drill pad site, taking over half a football field. So at the moment, the largest geothermal field puts out about 800 megawatts. And the expectation is if closed loop geothermal takes off, that'll go over the gigawatt.
All right, we've got one last question, it looks like, from the internet, which is good because we're right on 7 o'clock. Somebody else asked one. The question is, has anyone explored for geothermal in Tasmania yet? I'm not sure of the premise of that question. Is it easy to get acreage for exploration activities? Because this is about further.
Yeah, well, people have, the work that's just been described was done under a license. This was done under a special license. It was the first time geothermal had been explored. Tasmanian Mines Department has been excellent. They even had categories for different. If you want to look for metals, you needed a category 1 license. If you wanted to look for coal, it was whatever category that was. And they then had a special category. So if we haven't thought of it, then let's just put it in there. And this geothermal license, the initial one, which covered a third of the state, was a special geothermal license. And that was done under that granted license, and then it got reduced and reduced. But in Tasmania, certainly, and you can apply for a geothermal license and you would probably get it.
Sorry, that question was from Jess Godfrey. I forgot to mention. Thanks for that. One last question. I think this is a really good question to wrap things up from Tobias Stahl. Is there a timeline going forward, and is there any interest from political stakeholders and developers? There is an election coming up, John.
Yes, there is. Look, there has not been a lot of interest here in Tasmania. Where the hydro has said, look, we've got a lot of renewable energy. We do hydro. We're going to do pumped hydro, and at the end of the interview, the chap we talked to said, look, this has got to be one of the best projects. I'm fascinated. It's brilliant. I really hope it goes ahead. It's not going to be us. But you get used to that. And ARENA, I've had several people, ARENA's who put a lot of money into geothermal 10 years ago. But in the last couple of years, I've had several people come and say, look, I'm very close to ARENA. They'll be saying, this is a great project. Why can't we, show me why I can't put money into it. And we've had things that rather you didn't apply because refusing can offend. But there are new geothermal methods coming out, and I think it might be time again. But if the question was timeline, I won't commit.
How long is a piece of string?
How long is a piece of string? Yeah.
Well, excellent. Thank you so much, John. That was a fantastic presentation
Thank you.
and great interaction from online and in here. I will wrap this bit up by a comment from Andrew Long. Thanks to John and ASEG Tasmania and GSA Tasmania to allow us to piggyback on the scheduled talk as the first in hopefully a monthly ASEG webinar series.